In this video, I'm going to show you how to use the correlation matrix. Here we have a trivially simple model where we have three sizes of rocks and we simply add up the total number of rocks. But the number of rocks is variable and I have used the normal distribution to define that. So we have a mean of 100 and a standard deviation of 10, and you can check how the mean and standard deviation change as I move down the rock size. We need more small rocks than we need big rocks. Right now, the way the model is set up, each of these distributions is statistically independent from the other. So right now, if you take a look at big rocks, that's a below average value. Medium rocks is above average, and little rocks is well below average. And if I hit F9, we get a different distribution of rocks for each. I've got below average rocks for big and medium and above average for the little rocks. And so it would go. But every once in a while, in reality, we run into situations where variables are not statistically independent, where they move together. So we're going to imagine that we're building something. And the more big rocks we use, that means we're going to need more medium rocks. And needing more medium rocks means we're going to need more little rocks. And of course, the opposite logic would apply as well. The fewer big rocks we use, the fewer medium rocks, and the fewer little rocks. So if I want to build in a relationship like this to make these variables move together, we would use the correlation matrix. So you're going to have much more complex models possibly, but all you have to do is identify the variables that are correlated, as I've just done here. Then you go to the define correlations icon, click on it, and we get a matrix that comes up. I'm going to rename mine rocks. And down here you're going to see in the columns we have big rocks, medium rocks, little rocks, and in the rows we have a repeat. Across the diagonal we have the number 1. This means big rocks is perfectly correlated with itself. So what I'm going to do here is I have big rocks and medium rocks. This number is 0. 0 means there is no statistical relationship between these two values. And I'm going to change that. I'm going to say, yes, there is. There is a positive relationship, and it's relatively strong. So I'm going to put in a 0.8. For the purposes of this demonstration, I'm just making up the 0.8. But for your models, you would have presumably a more compelling reason for choosing a value. And the value you choose would have to be between a +1 and a -1. Positive values indicate that the variables move together, and the larger the number, the closer the movement of the two variables. If we have a negative relationship, that means these values move in the opposite direction. And the closer that value is to -1, the closer these variables move together, although in the opposite direction. So now we're going to talk about big rocks and little rocks, and I'm going to say that's highly correlated also, but let's make it a 0.7, just so you see that it can be different. And now over here I have big rocks and little rocks, big rocks, medium rocks, big rocks, and big rocks. And now I'm going over here to medium rocks. This matrix will always be symmetric. So when I put in a 0.8 here, a 0.8 occurs here. This is still the point. This is still 1. And so I'm coming down here to say, what's the correlation between medium rocks and little rocks? And let's say, let's make that in between the two, 0.75. Okay? So my concern in this video is that you know how to use the correlation matrix. In reality, when time comes for you to estimate these values, you should have more than the make up the number approach that I'm using right here. Okay, so now we're going to say OK. and it says select a location for the matrix. And I'll say, okay, I can do that. I'll say put it right there. And it puts the matrix right there. And now, let's see if we can close this. Hide the comments. Now when I hit F9, I would tend to see a bit more of a correlation. Now you're not going to see an absolute correlation where we're always going to have above average values for one, means above average values for all others. But what you're going to see is that over many iterations, that the relationship in the size is going to statistically bear out these numbers here. So if I come on over and I've already made this an output, let's just use a simple number of iterations, 1,000. And we will take a look at this. Is the number of rocks that we might have. This variable right here is the output, and it comprises the sum of these three values. So what we have done is we have basically gone into the model and influenced it by creating this correlation matrix. We have basically said, I want this number and this number to move together. And I want this number and this number to move together. And I want this number and this number also to move together. And I have specified the strength of that togetherness. So once again, that doesn't mean that you won't hit F9 and get numbers that look like they're all over the place. But when you do a series of iterations, when you do a simulation with a large number of iterations, it is going to conform to that correlation matrix that we just created. So this is an important way when you're building a model. When you have variables that need to move together, you can make them move together. So in a model, you could have many different correlation matrices. You might have rocks that have to move together, but in another part of your model, you might have values that move in the opposite direction. So you can have any number of correlation matrices in a model, and it's a very useful tool to keep in mind as you move ahead to build your own model.